Greetings and welcome, friends. Mr. Waddy here. We are talking about section 3.2. We were talking about functions yesterday, where for every input there was exactly one output, and today we're talking about what's that say? Linear. We're talking about ears. No, that's line R. Linear equations, linear functions specifically. This is going to be good stuff. Remember back in the day when we were doing literal equations, where we had multiple variables and we had to solve for one of them? All of those skills are coming back, guys. This is going to be amazing. We're going to spend a good amount of time learning about lines. So good. So linear equations are equations that represent lines. A linear equation in two variables, x and y, is an equation that can be written in the form y equals mx plus b. Oh, wow. Good times. We're going to talk about that. Oh, I'm so pumped. Where m and b are not variables. M and b are constants. So you can think about m and b as being nombres, mis amigos. Those are just numbers. But x and y are my variables. So I might have like y equals 3x plus 2, for instance. The graph of a linear equation is a line. Who would have guessed? Linear line. I guessed it. Likewise, a linear function is a function whose graph is a non-vertical line. Why do you think a vertical line isn't a function? Because it would just forever fail the vertical line test. Like it just infinitely fails the vertical line test, right? So a linear function is a non-vertical line when you have a linear function, okay? A linear function has a constant rate of change and can be represented by a linear equation in two variables. Okay, so functions are consistent in their change. So they're going up 1 over 2. They're going down 3 over 5, right? They're doing the same thing consistently, okay? It says this: a nonlinear function does not have a constant rate of change, so its graph is not a line. Nonlinear, not a line. That makes sense. Okay, so here's an example. Let's see if we can identify linear functions using graphs. Does the graph represent a linear or non-linear function? Explain. So here we go. I've got this shape. This is actually called a parabola. And notice this. Look at this. Okay. So it looks like from this point to this point on the grid, I go down 3 and over 1. And so the next point I would expect, if it's linear, would be down 3 and over 1. And then it just juked me. What? Who's been playing Madden? Someone just juked me. I completely did not expect that. I was following this linear trend. And no, this is a curve. This is non-linear. Okay? Non-linear. Because, yeah, it's all swoopy and curvy and such. Non-linear. Whereas this over here is a linear function. Because notice, like, if I just pick some points on this line, you'll notice that it's got a constant rate of change, right? Constant and change sounds like an oxymoron, I understand, but check out what's happening. It's going from point to point, it's going up 2 and over 1, and up 2 and over 1, and up 2, and it's just constantly doing the same thing. Right, and I would expect this pattern to continue forever in that direction. And also notice how liney this looks. This is the most liney graph that you've ever seen, right? I think you'd agree. This is a line. It's a straight line, which is what we're talking about, linear functions. Also, do you think this is a function? Does it pass the vertical line test? Yeah, only one output for every input. So yeah, it's even a function there. Let's see. Let's look at example 2. Identifying linear functions using tables. Oh, wow. Okay. All right. Does the table represent a linear or nonlinear function? Now, linear functions, they said, had a constant rate of change. Okay? So I'm expecting to see a pattern in the way that it changes. So, okay, let's look at just the x's. Notice this. 3 to 6 is plus 3. 6 to 9, what's that? What's it changing by? Add 3. 9 to 12, how do I get there? Add 3. So the x's, the inputs that I've chosen for the independent variable, happen to be consistently apart. And because I've done that, I would expect that the outputs will also be consistent. Okay? So let's see. Looks like this is decreasing. This is minus 6. To go from 30 to 24, what was the change? Looks like also minus 6. And 24 to 18 is also minus 6. So far it looks like it's going down 6 and over 3, right? Because the y is the up and down, if I'm thinking about rate of change. So this one would have been, graphically speaking, down 6 over 3. But notice it's constant. It's changing by the same amount every time. So we would call this linear because it has a constant rate of change. Right? It's changing by the same thing, todo de los tiempo, all of the time. Same thing. Good stuff. All right, let's look at part B. 1 to 3, what's the change? So it's adding 2. 3 to 5, 2. 5 to 7, 2. Okay? So when I pick my inputs, if I'm going to be examining a function to see if it's got a constant rate of change, I need to pick inputs that are equidistant from each other, right? They have to be constant. And now I'll analyze the y, okay? So let's see what happens for the y. It looks like from 2 to 9, it's going up 7, okay? From 9 to 20, is that plus 7? Uh-oh. That's like plus 11, actually. Yeah. Okay. And then let's see, what's this? Plus 15. 35 minus 20 is 15, and so that was going up 15. So this is nonlinear, okay, because its rate of change was not constant. The rate of change was changing, right? So it was not constant. Right? You guys buying this? You feeling it, Mr. Krabs? Are you feeling it? Yeah. Let's take a look at I just want to quickly glance at 2 more graph ones just to rehearse this concept. All right, does the graph or table represent a linear or nonlinear function? All right, what do you guys think about this one? Linear, I agree. It's a line, okay? It's going up 1 over 2, up 1 over 2, up 1 over 2. Constant rate of change. Is this a function? Does it pass the vertical line test? Yeah, it's also a function. Cool. Question, comment, yeah. Well, what I'm doing, I'm actually picking the points on the grid, okay? So what I was aiming for was when does the graph hit the crosshairs of the grid? All right, those are actually called lattice points. And then, so I'm thinking of to move from one point to the next, what did I have to go up? All right, and then what did I have to go over? Thanks for asking that, because yeah, you're right. It looked like I could have just randomly been picking that. All right, let's look at this other one. So here I'm picking some lattice points. All right, so between those, I would have to go down 1, over 1, down 1, over 1, down 1, over 1, down 1, if this was linear, I would have expected this to continue in that direction. Now, I realize this is made up of parts that are line-ish in appearance. They're straight, they're at least not curvy, but it's not linear because suddenly it went ba-doing and like ricocheted off this wall, and it is no longer a line. By the way, so this is non-linear because it doesn't have a constant rate of change. Is this a function? Yeah, it only has one output. It would pass the vertical line test, one output for every input. This is actually, if you wanted me to tell you, this is an absolute value graph in 2 dimensions. So this is an absolute value function. At the end of this chapter, I believe we'll be graphing these. So you'll actually have some experience with that later on. Let's see, let's look at example 3. All right, identifying linear functions using equations. All right, example 3. Which of the following equations represent a linear function? Explain. Okay, y equals 3.8. So let's see, y equals 3.8. If I wanted to think about that as a table, x, y, 1, 2, 3, 4, the y is just 3.8 no matter what, 3.8, 3.8, 3.8, 3.8. So as this goes up 1, it's going not up or down by anything. It's just like stay the same. Up 1, stay the same. Up 1, stay the same. This would actually graphically be a horizontal line that passes through 3.8 on the y-axis. This is a linear function. All right, it's constantly the same. Okay, you guys haven't even seen this symbol yet. Does anyone know what that symbol is over the x? It's like wearing this little hat. It almost looks like a long division symbol. It's actually a square root symbol, but this is nonlinear. The graph of that actually looks like this. It's a crazy graph. It's like a sideways parabola half, which is weird. So it's nonlinear. X is going to change all over the place. So is y. Check out this next one. 3 to the x is actually going to be non-linear. That's x as an exponent. That's weird, right? What's going on there is my variables in the exponent. So I'd have 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. That graph would actually just like hyper escalate. It's non-linear. Basically, for linear equations, what I'm looking for is if it's equal to thank you. If it's equal to a constant, actually more specifically, we would call that a constant function. But it's got a line. It's a constant rate of change. And then over here, like these graphs are going to be all sorts of crazy. Let's see, y equals 2 over x. I can't even remember what that graph looks like. I think it's like this. So this is nonlinear. Earlier, remember what did we say a linear equation looks like? They said y equals mx plus b. So if it's not some number being multiplied by x plus a constant, it is not a linear function. So like I can't have a variable in a denominator. I can't rewrite that to look like that. I can't have a variable under a square root or in an exponent. I can't have x being squared. There's no exponents besides 1 here. How about this one? You guys think that's going to be linear? Now check this out. What if I distributed this? What if I write that as y equals 6x minus 6? That's actually linear. All right, that was the only other linear one there. And then this last one is non-linear. All right, well, thank you for watching, internet friends. We'll do some more of this mañana. Have a great day.